กลับมาสู่เซสชั่นช่วงบ่ายนะครับของวันนี้นะครับด้วย Keynote Speaker คนแรกนะครับของช่วงบ่ายนะครับผมภูมิใจอย่างยิ่งนะครับที่ได้มีโอกาสที่จะแนะนำ Keynote Speaker คนนี้นะครับเพราะว่าท่านเองก็เป็นอาจารย์ของผมเองนะครับที่ AIT นะครับผมเป็นลูกศิษย์แกตอนปี 1994 นะครับที่เข้าไปเรียนที่ AIT นะครับกำลังนึกว่าจะพูดภาษาไทยหรือภาษาอังกฤษดีนะครับก็ได้ทั้งสองภาษาเอาภาษาไทยแล้วกันนะฮะเพราะว่าพวกเราจะได้เข้าใจกันง่ายๆนะครับอาจารย์เบอร์กาโดนะครับเป็น professor นะครับ emeritus professor เนี่ยก็ถือว่าเป็นศาสตราจารย์กิตติคุณนะครับก็คือสูงขึ้นไปอีกกว่า professor หรือศาสตราจารย์ปกตินะครับที่ AIT นะครับปัจจุบันนี้ท่านเกษียณจาก AIT แล้วนะครับแล้วก็เป็นผู้เชี่ยวชาญด้านธรณีวิทยาธรณีวิศวกรรมนะครับที่บริษัท Index International Group นะครับก็ช่วยงานในของบริษัท Index ในหลายเรื่องนะครับรวมทั้งเรื่องรถไฟฟ้าต่างๆนะครับอาจารย์จบการศึกษานะครับปริญญาตรีนะครับวิศวกรรมโยธานะครับจาก Mindanao State University นะครับที่ฟิลิปปินส์นะครับจบปริญญาโทนะครับ Master of Engineering นะครับที่ AIT นะครับแล้วก็ได้ทุน Fulbright นะครับไปเรียนต่อนะครับที่ปริญญาเอกนะครับที่อเมริกานะครับที่ Utah State University นะครับที่อเมริกานะครับไปเรียนกับ Professor Anderson ซึ่งไปมาผมก็ไปเรียนกับ Professor Anderson ด้วยเหมือนกันนะครับเพราะฉะนั้นผมเป็นหลานปู่นะฮะไปเรียนกับแกอีกทีหนึ่งนะครับประวัติทางด้านงานวิจัยของแกนะครับถ้าฟังแล้วก็จะตกใจมากนะครับเพราะว่าไม่นึกว่าคนหนึ่งคนจะทำได้ถึงขนาดนี้นะครับอาจารย์ publish หนังสือไป2 เล่มนะครับแล้วก็มี chapter ในหนังสือเนี่ย7 chapter นะครับเป็น editor ของหนังสือเนี่ย22 เล่มนะครับมี research report เนี่ย42 research report นะฮะมี journal paper 150 journal paper ไอ้ของเราจะ paper หนึ่งก็จะแย่ลากเลือดแล้วนะครับต้องใช้เวลา150 ปีถ้าเป็นผมนะฮะกว่าจะครบเหมือนนั่นแกนะครับ conference paper 300 conference paper นะครับผลิตนะครับปริญญาเอกไปแล้วนะครับ17 คนนะครับ17 คนก็คูณเข้าไปนะคนละกี่ปีนะฮะก็พอสมควรนะครับปริญญาโทนะฮะ160 คนนะครับเยอะมากนะครับเพราะฉะนั้นผมเชื่อว่าหลายคนในห้องนี้ก็เป็นลูกศิษย์แกนะครับนะฮะที่น่าสนใจคือข้อมูลนะครับก็เรียกว่าเป็น Scopus Science Citation คือการอ้างอิงงานวิจัยของแกนะครับในปี 2015 นะครับมีทั้งหมด 2,329 citation นะครับนะฮะสำหรับ Scopus นะครับสำหรับ Research Gate ก็ประมาณ 2,997 ประมาณ 3,000 citation เยอะนะครับก็คือมีคนอ้างอิงงานที่แกทำนะครับเพื่อจะไปใช้ต่อนะฮะของผมนี่ไม่รู้มีถึงสัก3หรือเปล่าไม่แน่ใจนะครับมีใครมาอ้างผมบ้างหรือเปล่าก็ไม่แน่ใจอันนี้ 3,000 นะครับนอกนั้นแล้วนะครับแกก็เป็นอลัมไนนะครับดีเด่นนะครับของทั้ง AIT แล้วก็ทั้ง Utah นะครับที่แกได้จบมานะครับแล้วก็เป็น Council Meeting Member นะครับของ IGS นะครับ International Geotechnical Society นะครับดังนั้นเนี่ยนะครับวันนี้นะฮะท่านจะมาแชร์ประสบการณ์นะครับในงานที่ท่านทำในประเทศไทยเป็นหลักเพราะว่าตั้งแต่จบปริญญาเอกมาเนี่ยท่านก็กลับมาทำงานที่ AIT นะครับแล้วเราก็รู้ว่า AIT เนี่ยก็เคสการศึกษางานวิจัยต่างๆเนี่ยก็ล้วนแต่อยู่ในประเทศไทยนั่นแหละนะครับเป็นส่วนใหญ่นะครับผมยังจำได้เลยว่าในช่วงท้ายๆที่ผมเข้ามาช่วยอาจารย์เนี่ยนะครับหลังจากจบปริญญาโทแล้วเนี่ยก็ได้ไปทำสนามบินสุวรรณภูมิในช่วงที่ยังไม่เป็นสนามบินยังเป็นหนองงูเห่าอยู่นะครับนะซึ่งอันนั้นก็ลำบากมากนะครับต้องเข้าไปในดงงูเห่านะครับแล้วก็ไปทำการก่อสร้าง full scale test เพราะฉะนั้นวันนี้เราโชคดีมากๆนะครับแล้วก็ให้พวกเราปรบมือต้อนรับท่าน Professor Bergado ครับ
Thank you very much for nice introduction and thank you for your invitation here. I have been in Thailand more than 30 years, but I cannot speak Thai, so sorry, I speak English. And I have been in EIT. The EIT system, very good. You have only graduate students. You have opportunities for research. We have selected students, smart students, innovative, creative students, and motivated students. And one of them is Dr. Sotisak. So I've been lucky to have excellent students in 30 years in EIT. And at the time, ground improvement, geosynthetics, new to Thailand. So it was a very good opportunity for doing research. So I like to stand up. It's nice to lecture when you're standing up. So the topic today is about development of ground improvement. And for soft ground improvement, I'm just citing two methods. One is prefabricated vertical drain, and the other one is deep mixing cement mixing method. And ever since I published my book in ASCE, Soft Ground Improvement, and it's from my teaching notes and from the help of my graduate students. So we are actually lucky for EIT to be in the central plain of Thailand, where you have soft Bangkok clay. And during the development of Suvarnabhumi Airport and expressways here, and luckily they use soft ground improvement, which is more economical. And if you look at the soft Bangkok clay, it's quite normal soft Bangkok clay with water contents around 100, and the undrained shear strength around 1 ton per square meter or 10 kPa, and salt content, which is normal here, is not abnormal, and the organic content is also normal, about 4-5%. Is good for deep mixing method of cement. Our first project for the PBD was the cobra swamp, Nong Mu Hao, and at that time it was just fish funds, and bulldozer has problem leveling the ground, except when it is dry in the summertime. And what is the beauty of the soft Bangkok clay is quite uniform. You compare it with the other clays, like in Vietnam, there's a lot of lenses of sand and silt, but this one is quite uniform, solid, soft clays, and about 10 to 20 meters thick, continuous, north-south and east-west, for 200 by 400 kilometers, big deposits. And down below is the steep clay and the medium clay and the dense sand. So to improve the soft clay, because there's a lot of voids, and this void is occupied by water. And we have to take out the water, because the water is the enemy of the clay. If the less water is stronger, more water is weaker, but the permeability is very small. So the objective is to reduce the voids. And from here, higher voids to here, lower voids, or you pre-compress. But you have to use some artificial drainage so that consolidation, which is normally vertical, takes time because of permeability very slow. So we have to put in artificial drainage, which is the prefabricated vertical drain. So what is PBD? It is artificial vertical drainage. The purpose is to shorten the drainage path so that consolidation will be faster. And in order to squeeze out the pore water from the clay, you need a surcharge. Water will not flow up against gravity. it has to have a hydraulic gradient so that it will flow up. And we use horizontal drainage between vertical drain, which is higher than the vertical permeability because of the sedimentation of the clay. Horizontal permeability is higher than the vertical. So we use that one. Then the vertical drain will take care of the vertical drainage. That's why it's called vertical drain. So surcharge embankment usually using soil embankment. However, they say, oh, this one takes time, about 1 year. No, time is money. You want faster than this. So now vacuum pressure is to make it faster. You suck the water out, connect it to the vertical drain. And the latest one, before I retired, we found that applying heat combined with PVD called thermo PVD is quite promising. So if you use vacuum, maybe you reduce time by 30%, 50%. But if you add heat, you will decrease further. And because the clay permeability increased with temperature, because the viscosity of the water reduced. So that is original. This is our original, applying heat, which I don't have a patent because applying patent in Thailand is expensive. So this is the principle. You put vertical drain, so the water will flow to the vertical drain. You have a blanket here, and Suvarnabhumi, we put drainage pipe, so to take out the water coming out here, and the surcharge. And this surcharge must exceed maximum pass pressure of the clay. And so it has to be 3.5 meters high. Cannot be only 2 meters. So this principle is you have the original ground, you put in the drain, put surcharge until it settle, compress or pre-compress, take out the extra surcharge. So 1 is here, 2, then 3 here, you pre-compress already, compression. And then when you take out excess surcharge, you have a rebound a little bit. When you use for the runway or road, you have only or you remove compression. Primary compression consolidation must be complete. The remaining one is only secondary compression. So if you don't use vertical drain, it might take long time for compression. Consolidation can be about very long time. But if you have vertical drain, you might finish in a year. Or if you have vacuum, less than that. And if you have heat, even more than less time. But since you are building embankment in a soft ground, then you have to have stage loading here. And that takes time. This one alone takes already almost 6 months, another 6 months. So a year is already wasted if you don't use other methods. So these PVDs come from the original sand drains. However, for the sand drains, sand is expensive here. The source is 100 kilometers away. The diameter is quite large, and the smear zone is twice the diameter. Imagine the smear zone here. I will show you later what's the problem. But for PVD, it's just a very small cross section. The mandrel is also small cross section. So this is the PVD. It's made of polymer, geosynthetics. It has a filter around the core. The filter allows water, but prevents or minimizes the soil particles to go into the channel of flow, which is the function of the core. Core is channel of flow, prevent buckling, supports the filter. The filter allows pore water minimize fine particles, react against horizontal pressures. So there are many types, but this design is quite okay. And even though it's deformed, twisted, this size, shape of the core, and another one is quite good to resist buckling and deformation. So this PVD is supplied in rolls. This is a mandrel. Push it down. You cut it. One location is less than a minute. And you can install. So less than a minute. So you can install quite a lot in one day per machine. The pattern is square or triangular. And since we have only very shallow thickness, we can use a modified backhoe to install it to around 10 meters. The plate is here. So the plate serves as an anchor. When the mandrel is withdrawn, we cut it and finish one location, 50 seconds, less than a minute. The problem is the installation. The installation here causes some smear or disturbed zone. And this disturbed zone permeability Ks is lower than the original horizontal permeability. And the Ks over Ks is a measure of the disturbance. So this is a barrier of flow to the drain. This is the drain here. QW discharge capacity. And if you have the mandrel, the drain is here, the mandrel around the drain, it will create disturbance twice the equivalent diameter of the mandrel. So this disturbed zone has to be minimized. This is the object of research. How do you neutralize the effect of the smear zone? Because it is a barrier of flow. So one method is electro osmosis. You put electric here, negative, positive. The ions flow from positive, negative, bring the water molecules with it. But since this will be drying, this is wetting, so you reverse the flow every 24 hours. And this has been tested, but not so successfully, but it is ongoing. This is quite sensitive to salt content and organic content. But we have done this in the lab. We have a small diameter, small cylinder, large cylinder, and we use the voltage of 60 and 120. These are direct current. And you can see we use copper, electrode, and carbon. You can see PVD only, and if you use electro osmosis, it's faster and more. The N of primary is achieved faster than without it. And that is, and some people are using this for field tests. Ours is only laboratory test, undisturbed sample, reconstituted sample. And another one is vacuum. So you drain, you either connect direct to the vacuum, or you have a membrane and you connect the vacuum at the embankment. And here we reduce the pore pressure without increasing total stress. So you don't have problem with stability, or you don't have stage loading problem. And it also increases the effective stress by reducing the pore pressure. And in this case, we have then the diagram is put the PVD here in this big cylinder and apply vacuum. You have vacuum generator and air pump. And so that is the diagram for in the laboratory. You have reconstituted clay, PVD connected to vacuum. And we can also apply normal load here by the balloon or airbags. For the thermo PVD, we found that when we increase the temperature up to below the boiling point of the water, 90 degrees, permeability increased by almost 4 times. Because the viscosity of the water reduced, so this is permeability at room temperature, permeability at higher temperature, and because of that, there is increase of permeability. And this is the schematic diagram for thermo PVD. We put the special electric wires into the PVD. Then we have the electric generator, and then we apply heat. And this is the drain with heat, and we measure at some distance from the drain the temperature to check the heat transfer. And you can see that after 24 hours, temperature already stabilized. So it's stabilized very quickly. So we do the test PVD only, vacuum PVD, thermal PVD with special electric wires, and thermal vacuum PVD, combined thermal and vacuum. And we have this test before flooding in our lab. It was okay. After flood, this will destroy it. But we have done our testing. And this is the special wire we put inside the core. So for the heating, and this is the result. PVD only, you see the settlement or compression with time. PVD only. PVD with vacuum, you have a little bit faster. PVD with heat, quite fast. The difference here is the secondary compression. PVD with heat and vacuum. So you can see the advantage of applying heat compared to vacuum. And I have seen in the States, somebody say, hey, Professor Bergado, yeah, your paper was good. We use it to clean up the wine or mine waste. And we use steam to heat the PVD, steam. And you can also use here some fiber optics to heat inside the PVD. So if we look at the smear zone, that one, the zone near the PVD is here, and this is the smear zone, which is twice the equivalent diameter of the mandrel. And you can see the temperature average here around 80 degrees. And that would increase the permeability. You can see the measurement of shear strength by miniature shear, bane shear. You can see the increase of the bane shear quite high. We can also model this one, and this is our modeling, or you can use equivalent vertical permeability using this equation, or the axisymmetric model, and you can see the flow of water as it consolidates. This is axisymmetric, this is equivalent permeability, and both of them give quite good agreement with the simulated and the measured data. So we can use that one. And from here, we can also back calculate KH over KS and CH. These are the very important parameter, flow parameter. KS is permeability of the smear zone. KH is the original horizontal permeability. CH is the horizontal coefficient of consolidation. So From this method, we have here normal PVD, vacuum PVD, thermal PVD, thermal vacuum PVD. And this is our simulated and measured data. And this is our CH. For normal PVD, CH is small. This is reconstituted. In the field, will be around 5 meters squared per year. And then vacuum increasing. Thermal, even more higher. Thermal vacuum. And the KS over KS is reducing, almost equal to 1. So we almost erase the effect of the smear here, only 10% remaining. So if you combine vacuum and thermal. So KS over KS is a measure of the disturbance. And for us, that is already a good indication of success. Although you cannot combine this, it's quite uneconomical. But you can see effect of vacuum and thermal is already registered. Increase of horizontal coefficient consolidation, which measure the rate of consolidation or rate of drainage. And KS over KS measuring the effect of the smear or distal zone. Now we go to the field. This is at Suvarnabhumi Airport. And they have both, in the runways, they have the ordinary PVD, in some areas, vacuum PVDs. And this is for ordinary PVD. Of course, we have to use surcharge and bench stabilizing berm to prevent sliding. And the time C2 drain, they use direct connection from the drain to the vacuum. Of course, there are two types. One is membrane method, which is not direct connection, but this one is a direct connection without membrane. And because of conventional PVD, you have to go more than 4 meters, so you want to exceed maximum pass pressure. But for vacuum, you only need around 2.8. And you can see this is the ordinary PVD. You have some stage loading, but this is a vacuum PVD here. It's faster than the ordinary PVD. Now we go to EIT. At EIT, we have a stronger clay than in Bangkok. We have our undrained strength here, which is 15 to 20. In Bangkok, we have only 10. And we use this one to test the thermal PVD. We only instrument the middle here. Out of 9 PVD, we only instrument the middle, because that is our principal objective. How to put heat. We have a heat exchanger for the room or the building from the Suvarnabhumi Airport. Exists tube, PEX. And you put hot water here and it will transfer heat. So we use that one. And we have a solar here, a pump. And we have here insulation for the water, hot water go inside. And we test 2, one without heat and one with heat, same height. So we have water storage in the daytime. We use solar cell. Nighttime we use electric heater. And circulate water. It has to be circulated. If not, the temperature reduces. So circulating 24 hours. And you can see the settlement without heat. With heat, quite fast. At 3 meters, at 6 meters, at the surface. Excess pore pressure. Because water expands more than the clay structure, excess pore pressure, water expands, so there's excess pore pressure at near the vertical drain, but then the vertical drain will take it out. So it's quite, if you don't have vertical drain, this will weaken the soil, the clay, when you heat. But if you drain it out, make it stronger. And you can see the heat transfer in the beginning, after 20 days. So it's quite quick transfer of heat from the location of the PBD with heat. And the CS value here, normal, vacuum, and here is thermal PBD. You see, I will look at the why they are high here. See, you can see the CS value increase like in the lab. And the KS over KS, some of them are, but this one is more realistic. In the field, you cannot control it because it's in the field, actual field test. What is the advantage in Thailand is cheap land and labor and material. You can do field full-scale tests. And you don't need a centrifuge. Centrifuge is when you have a built-up city where you cannot do a field test. And centrifuge is good, but you need, for industrialized countries, then they use a centrifuge. But Chai, my student in Japan, my only student from China, brilliant doctoral student, found that there is effect of non-uniform consolidation. CH or CB is a function of KH and MV. And when KH and MV reduce, but the CB or CH almost constant. But Pyra, a researcher, come out with, if suppose you have two types of clay, this is impervious, this is free draining, drainage going that way. This higher permeability, lower permeability, called A/B. And reverse here, more higher permeability, lower permeability, called B/A. And excess pore pressure, you can see the AB case have more excess pore pressure than the BA. That means this is faster consolidation, smaller. But if this is your uniform, only one kind of clay, this is the result. So these two here with different permeabilities are non-uniform. So there is an effect of the non-uniformity with the excess pore pressure. Because permeability is function of the void ratio. So the more compression, the void ratio is small, permeability becomes smaller. So smaller E and smaller K, smaller void ratio, smaller permeability. That is the non-uniform domain. For example, you compare one-dimensional loading, drainage, here is impervious, to the drain, which is axisymmetric. This is a PBD unit cell. And these are the parameters. CH is constant, ideal condition, no smear, no well resistance. And you have this result. For the PBD unit cell, compare with analytical and numerical, and this is for one-dimensional. You see the difference. This is due to the effect of non-uniform consolidation. Now, we take the variation of permeability with the radius, free strain, equal strain, and radius, this is the drain is here, the void ratio, smaller, because now this is draining, then away from the drain. Or if you have the PBD here, permeability near to the drain, permeability far from the drain. This is the smear zone. So Kr is less than Km. And if you take the ratio, Km over Kr, this is the smear zone. That is the effect of disturbance due to the installation of PBD. So for ideal condition, you should have this degree of consolidation with time, but the real one is here because of the smear. And if you back calculate here, what is KH over KS is 2.4. So without smear, you don't get the actual result of the test because there is a smear zone. And this smear zone was done by my student in 2011. There is smear. Cholachat, also my previous student, now working with Prof. Indaratna in Australia, says water content near the PBD is lower. So that is the cause of smear. However, Professor Chai says there are two kinds of smear zone. One is mechanical, is one by non-uniform consolidation. One is direct measurement, one is non-uniform consolidation, and this is the subject of research. There are so many doctoral degrees obtained by looking at the smear zone. And this is another way of looking at it. There are two kinds, two components of smear zone. One is the mechanical, and the other one is non-uniform. And this paper has been accepted in Geotechnical. Example, the back-fitted field KH over KS in this by Chai and Miura is 10. Ariake clay measured KH over KS is 5. If you use that, you non-uniform consolidation 2.4 multiplied by 5, you have 12, which is almost the same as 10. That is one of the confirmation why you have more back-analyzed KH over KS. That is under research. So this is conclusion for PBD. Sorry, I have two topics, so we are still in PBD. So largest increase in the shear strength within the smear zone, and the hydraulic conductivity smear zone increase due to heat and vacuum, and you have faster consolidation. Now is another one for field, the permeability of the smear zone increase due to the increase of temperature caused by the reduction of viscosity of the pore water. Now we go to the next topic, deep cement mixing. And we did, when you do, before you do mixing of clay, and if you increase the cement content here, 5, 10, 15, 20, the same water content. So you have the lower, the higher the cement content, the higher is the unconfined compression strength. And the higher the water, the lower, the higher the water content, the lower the unconfined compression strength. And we use a trial and error before. For the base clay is only here. When you mix sensitive to water content and to the cement content. Usually in the field we use 10 to 15% cement. And yield stress is a function of the unconfined, the yield stress is a function of the unconfined compression strength. And if we do one-dimensional consolidation, and we increase the water, the yield stress, which is here, reduces with higher water content. This is the original clay. And this is for 5% cement, 10% cement. When you increase the water content, the yield stress decreases. And it forms into one line. So we have the line of the yield stress. And here is the void ratio. So when we have that, we can predict the compressibility. This is void ratio, line of yield stress. And we can also predict the unconfined compression strength using this, a function of after curing void ratio and cement content. So we can now predict the strength and compressibility rather than trial and error if we use this technique. Second, there is optimum mixing water content. Is the total clay water content mixed in the clay over cement content. The total optimum is where it gives you the highest possible improvement in strength. Because when you have untreated clay, you have voids here, and there are some air in the voids besides the water. And when at high water content, there is a good mixing. At lower water content during mixing, some cement are unmixed. So there is inefficiency of mixing. So at high water content is efficient mixing. And we found that this efficient mixing or optimum mixing water content is close to the liquid limit. So if your ground water content is less than the liquid limit, you can see the contractors, they add water first. You put water first to the ground to increase the water content, increase to the liquid limit, and then start mixing. And that is so that you have a better mixing of the cement to the clay. So we have two. You can predict strength and compressibility instead of trial and error. The other one is the optimum mixing should be close to the liquid limit. Of course, if your ground is already close to the liquid limit, water content, then you don't need to add more water. But at EIT, we have only 80%, and the liquid limit is 100%, so we have to add more water for efficient mixing. Okay, there's a new one here. The effect of curing stress. During curing, there is, if you apply stress, then the voids are lower. See, this is a semi-log straight line. Here, higher stress, here lower stress. And so higher stress, you have higher unconfined compression. And this is due to the stress during curing. So our tests, we usually don't put stress during curing. So the improvement of strength due to no stress during curing is this. But if you apply stress, you have more increase of strength. This one 80 kPa, this one 0 kPa. So if you apply stress during curing, then you have more strength. I look at this. We have this full-scale tests using the deep mixing. And you can see here that the interaction is neither equal strength or equal stress. And I just show you that we derive the consolidation equation because of that. And we can see here that this is due to equal stress, due to equal strain. And to cut short time, we can simulate where this is from the field test. So we need to go, this is our objective. And if we have the right parameters, we can find this. This is clay, deep mixing, back analyze, coefficient vertical consolidation, ratio of permeability between the pile and the clay. And you can see 80% equal strain, 20% equal stress. So if you assume equal strain, which is now the assumption, you are in error only 20%. You can also back analyze the here modulus to get the negative skin fraction beta. And if we use that one, we can get spacing of the pile with beta, increasing spacing, increasing beta for negative skin fraction. And we can suggest that we can use deep mixing here to approach to the bridge or alternative to concrete precast pile. But the problem with deep mixing, there are low strength because there is failure. We call it pile failure. This one is soil failure. And if it is pile failure here, the measured bearing capacity for pile failure is lower than soil failure. And you will have this kind of failure or this kind of failure at the Sonapum Canal. And because of low, they even have added more piles here, but there is lateral shear failure. So what we do, we put some insert here called steepened deep mixing. Some people use concrete piles, some people use steel. Steel is more expensive. So after mixing installation, you put the pile and you hang it there until 14 days. And we measure the effect of the length and the diameter of the insert. The testing full scale. See, for vertical is a function of the length. This is 6 meter, 4 meter. And this one without insert, you can see the difference. This is deep cement only, this is with insert or steepened deep mixing. We also did the pull out, and we can now simulate. And the effect is the length is more sensitive. The ultimate bearing is sensitive to the length of the insert. And now the load transfer is more uniform than without insert. And the failure modes, you can see. And lateral load tests. We test horizontally without insert is here. But with insert, this is now sensitive to the cross-section. This is 22 by 22, 18 by 18. It's sensitive to cross-section rather than the length. So this is the effect. The cross-section have higher ultimate lateral than the length. So the length is, if the length is lower, then it affects, but when it is more than 4 meters, it has no more effect. So we have the field test, CDM, DCM is DCM, and compare the settlement. But this is one, CDM is DCM pile, surrounding ground, compared to DCM. So DCM has more lateral movement. But with larger cross-section, like 30 by 30, 22 by 22, you can see the amount of lateral movement. So that's all we have. These are the parameters back calculated. And with DCM only, construction quality is variable because of the mixing procedure. But to solve that problem, we use insert called SDCM and increase the capacity, both vertical and horizontal. And maximum load developed at the top, decreased to a depth of 4 meters. Therefore, the DCM failure occur at the top. No wonder there is a pile failure. But for SDCM, it is transferred down due to the presence of the inserted pile. And the ultimate load increased with lateral load increase with increasing cross-section, while for the vertical, capacity increase with the length. See here, the longer pile can reduce vertical displacement. The bigger sectional area reduce lateral movements. So thank you very much for your attention.
Thank you very much for your excellent presentation of the PVD and also cement column. I'm sure that all of you can see all the works that he have done and excellent work that contributed to our society. Thank you very much. And I'd like to give a token of appreciation to Professor Bergado in this occasion.